In this recording, I want to talk about the fundamentals of battery chemistry and go all the way through the chemistry associated with lead-acid batteries, which are probably the most common batteries that we use. Now, the basics, we define the Gibbs Free Energy, and it's the change in chemical potential for the active material in the battery plates. The Gibbs Free Energy is the maximum energy that we can get out of the battery, for the amount of material we have on the plates. There's some basics here. We're not going to get into this in any great detail. This becomes an electrical potential associated with the reduction of each element. We define hydrogen to have an electrical potential of 0. Based on hydrogen being 0, it turns out that copper is positive 0.337 and zinc is negative 0.763. So we can look up these potentials for different elements, and we can imagine what it would be like to create a battery from two different elements. So a copper zinc, the difference in the voltage is 1.1. So a copper zinc battery cell would have a voltage of 1.1. And theoretically that's right, but the true voltage down here, it's minus, you take what we would calculate and then you subtract off RT over NF times the log, and it's what goes in this part here is pretty complicated. There's the stuff that goes in there can be related to what we call cell overpotential. As we react out the area on the plates in the batteries, the reactive area that we have left decreases. The ion concentration in the electrolyte near the plate decreases or can change depending on how fast the reaction proceeds forward. And electrically, we just put all these things together and we pretend like the battery has an internal resistance. And so electrically we can model it as the voltage that we're going to get out of this battery is this V0 that we can look up from the tables minus the current times the internal resistance, for discharge. And the charging voltage is that plus IR. And from Ohm's law that voltage is equal to IR. So, this is how we can model it. We pretend like the battery has an internal resistance. So from this electrical model, we can say it's the charge efficiency, which is the Coulomb charge or amp hour charge efficiency, which will be near 100% for any battery that we're interested in. And then V minus IR over V plus IR to get the ratio of the discharge and charge voltage. And this is how we can bring this internal resistance model in and get the efficiency of the battery. The battery efficiency depends on the current that we're drawing out of the battery. I believe this comes from a lead-acid battery, but it gives you an idea that if we discharge very slowly, and charge very slowly, we can get a pretty high efficiency, 90-some% for very low charge and discharge. But as we increase the amperage, the efficiency falls off a lot. These are chemical reactions going on in the battery, and a chemical reaction is always endothermic or in one direction and exothermic in the other. So endothermic means it's absorbing some heat energy as you go through the chemical reaction, and exothermic means the chemical reaction is adding heat. The I squared R losses, or the internal resistance, are always exothermic and generate heat in the batteries. So a couple of examples. For lead-acid batteries, when we discharge the battery, the chemical reaction is endothermic. So the chemical reaction part is actually absorbing heat. Now the I squared R losses, due to the internal resistance, adds heat. And so at most normal discharge rate, lead acid batteries do heat up a little bit on discharge, but not too bad. But when you charge the lead acid batteries, that's when you get a lot of heat, because then the chemical reaction is adding heat and the I squared R losses are also adding heat. And so the batteries can get pretty hot on charging if you try to charge them fast. Nickel metal hydride batteries are the opposite. The chemical reaction that goes with discharging the batteries adds heat, and they can get really hot discharging, but then the chemical reaction will help reduce the heat when you charge them. Then we'll talk in detail here about lead acid batteries. I'm going to go ahead and do that as part of this lesson. The negative plate in a lead acid battery is made out of lead. Just the element lead is the part that is active. There are sulfate ions in the, it's a sulfuric acid is the electrolyte. So you have these sulfate ions as part of the sulfuric acid. And the chemical reaction is that the lead combines with the sulfate ion to make lead sulfate, and you get lead sulfate plates out on the lead plates. But that gives us an excess of 2 electrons, and that's how we're making the electricity. The electrons then go up the plates, and that's where the electricity comes from. On the positive plates, the chemical reaction is more complicated. The positive plates, the active component is lead oxide, PbO2. So the lead oxide, we need 4 hydrogen ions, and these are positively, protons. And then we need 1 sulfate ion, and we need 2 electrons to balance the charge there. So we have the +4 from the hydrogen, -2 from the sulfate, and then -2 from the 2 electrons, and that balances our charges. We end up with lead sulfate on the positive plates, and then there are 2 water molecules generated, and that's what's happening on the positive plates. So this gives us the total reaction that's happening as we're generating electricity from a lead acid battery. The chemical reactions go in reverse as we charge the battery. So as this lead acid battery is discharged, both of the plates are coated with lead sulfate. The sulfuric acid, we're using up the sulfate ions out of the electrolyte. So the acidity gets weaker as the reaction proceeds, and the specific gravity of the electrolyte decreases because we're pulling all of these sulfate ions out and putting them on the plates. So the state of charge can be measured by measuring the specific gravity of the electrolyte for lead acid batteries. And I've got this picture to try to help us sort of understand. Now, of course, in the real battery, the negative and the positive plates are very close together, but I've got the negative plate represented here, the positive plate represented here, and then the voltage across one cell will be 2.1 volts. And that's, if you look up lead and lead oxide, you're going to get 2.1 volts because of those 2 materials. We use sulfuric acid, so we have a lot of hydrogen ions or protons floating around in there, and we have a lot of sulfate ions in the electrolyte. Of course, there's also a lot of water in the electrolyte, and these dissociate. As we discharge, the sulfate ion combines with the lead on the plate to make lead sulfate, and then we have 2 electrons that go up the plates. On the positive side, we need 4 hydrogen ions, 1 sulfate ion, we get lead sulfate that plates out on the plate, and 2 water molecules that go back into the electrolyte solution. And to complete the charge balance, we need 2 electrons to come down. So you see we got 2 electrons going up the negative, 2 electrons coming down the positive. By making those electrons flow through maybe a light bulb or an electric motor, we can make use of that electricity up here on the load. And that's basically how the battery works, the lead acid battery. As we get near complete discharge, the plates get almost completely coated with this lead sulfate. And especially on the positive plate, which is the more complicated reaction, everything has to come together on an uncovered spot, and so you have to slow down the reaction as you get close to fully discharge. There's still a lot of energy, there's still a lot of space on those plates, but you got to draw it out slowly as you get close to full discharge. If you try to drive it too fast, you will get weird chemical reactions, like lead oxide, sulfite, all linked together, and it's really hard then to get these weird chemical reactions off the plate. So what happens is when your plates get coated with this weird stuff, then you just lose that area on your plate, and you effectively then have less charge capacity in your batteries. And as your battery gets old, this is what happens. Gradually the plates just get where more and more of the area on the plate is not active anymore. And then the battery is no good, and you go get a new one. There's 6 cells in a typical lead acid battery, and the cells are wired in series. 2.1 volts per cell gives you 12.6 volts when the battery is fully charged in a normal battery. One of those cells will be the weakest, and they're all wired in series, so whichever one is the weakest, it will get close to discharged first. And then what we usually do is we keep pushing charge through that cell, the other 5 cells, which then causes these interesting chemical reactions on the plates in the weakest cell, and the weakest cell just gets weaker and weaker until the weakest cell just really stops charge from flowing through there. And usually when a battery fails, it's because one cell failed, and the other 5 cells are probably fine, but because they're all in series, if one cell goes completely bad, then it's bad. For vehicles, we use deep cycle batteries. They tend to have fewer plates with thicker coatings. That just works out better if you're going to cycle the battery up and down a lot. We design in more positive plate area because the chemical reaction's more complicated, and that's the one that's probably going to die more than the negative plate. And slow charging, there are some pulse charging techniques that we can get back some of the chemical reactions, but in general, as the plates wear out, you just gradually lose capacity of the batteries. When we charge a lead acid battery, there's always some electrolysis of water because there's a lot of water in the electrolyte, and this comes out. This is where we get this apparent charge loss. It takes a few more amp hours to charge the battery than what we're going to get back, because some of those amp hours went into breaking down water into hydrogen and oxygen. And if you overcharge the batteries too much, you can actually boil all of we call it boiling the water out, but you can convert enough of the water into hydrogen and oxygen to deplete the electrolyte. Here's a similar one that shows you what's happening when you're overcharging. And what happens is you're driving the electrons now in the other direction, so the electrons are being driven down into the negative plate and being pulled out of the positive plate. So these excess electrons will combine with hydrogen ions to make hydrogen gas, and it'll bubble off next to the negative plates. And by pulling out electrons, you'll pull them out of the oxygen ions, and the oxygen ions in solution will come off as oxygen gas. And so this is the electrolysis of water. And I've got it here. The positive plates give off hydrogen gas, and the negative plates give off oxygen gas. So you keep thinking you're pumping more and more current into the batteries, but all you're doing is creating oxygen and hydrogen gas. And I'm going to go ahead and quit there to break it up.